I should put on.
Yes.
But that link is just to, yeah.
This is already on, right?
Yeah. That's already on.
Let me solve this topological problem.
Not.
Oh, okay. That's great. Yeah, it'll work.
That's for the room. That's on. It's coming into here. This is recorded. Thank you, everyone, for coming to our afternoon session. Our first speaker today is going to be Meng Cheng. He did his PhD at the University of Maryland, where he studied Maruyama modes. Then did his postdoc at at Microsoft in Santa Barbara, where I understand there's a lot of collaboration with UC Santa Barbara, and then joined Yale in 2016, where his group now works on quantum criticality, atomic phases, and symmetric topological phases. His title today will be Topological Defects and Anomalies. No, that's not right.
Close enough.
Defects and anomalies in lattice systems. Schultz, lattice, and Fletcher. Take it away.
Thanks for the introduction. Thank you. Thanks to organizers for inviting me to speak. I was a student in this summer school. That was 2009, so that was a while ago. So it's a great pleasure to be back again. I'll talk about defect anomaly in lattice systems, and the defects are topological. Part of the talk will be based on this paper written with Nadi Seiberg, posted last year. And I'll be very short on references on the slides, and you can find many references in the paper. Okay, so you might be wondering why I put these names together in the title. They don't look related at first glance, but if we think a little deeper, and that's kind of the point I want to convey, that they are actually related at some fundamental level. Okay. So 't Hooft, the reason I mentioned 't Hooft name is, well, no, it's not because he works on condensed matter or anything like this, it's because we're going to talk about anomaly, and we usually attribute this idea of using anomaly to analyze field theory to 't Hooft. And we'll see how that comes out. And the Lipschutz lattice, which I'll discuss in a couple of slides in great detail, is a celebrated theorem about the behavior of a low-energy behavior of a spin 1/2 chain, a Heisenberg chain, for example. Basically says a spin 1/2 Heisenberg chain cannot have a completely featureless or boring ground state. Now, Lackinger's theorem refers to the result that you have system fermions which form the Fermi surface, then the volume of the Fermi surface is fixed by the fitting. Okay? And this is an example of a more general sort of class of results known as a generalized Lackinger theorem. Well, at least I call it generalized Lackinger theorem. That says if you have a system with a finite U1 charge density, then again, it cannot be completely trivial. Something interesting has to happen. Okay. So the message, kind of the take-home message, is that I want to think about all of these as the consequence of 't Hooft anomaly, as long as we include lattice symmetry into the story. All right, so here's the outline of my presentation. So I'll first start from a review of the Lipschutz lattice theorem in the context of spin chain. Most of the talk will be about 1+1, just because it's simple and you see the essential features of the story already in 1+1. And then I'll discuss what does it mean to have a 't Hooft anomaly for global symmetry on the lattice. And then hopefully, if time permits, I'll discuss eminent symmetry anomaly. All right, So let's kind of step back and think about a little bit about the problem, at least many of the problems that we want to solve in condensed matter, or more broadly in quantum many-body physics, is a problem of emergence. Often you have some lattice model, you have some Hamiltonian, and you want to understand what's low energy theory, how it behaves at very large distance and low frequency. Right? Okay, so specifically, I want to focus on lattice model with local interactions, Haber model, Heisenberg model, etc. And a very common assumption, or belief rather, is that such a system often admits a nice description in terms of a quantum field theory, a continuum quantum field theory. And usually that's kind of the golden standard of understanding what's going on. You can understand it in terms of a nice continuum field theory. Okay. More precisely, we have, at least in theory, there's a kind of RG flow, or renormalization group, that take you from an ultraviolet system, a lattice model, to low energy theory at very long distance that captures the physics in that region. Okay. Of course, it's in practice, it's extremely difficult to solve this problem. Otherwise, we won't be doing what we are doing. And it'd be nice to have something that connects the information we have at the scale of lattice to what happens at low energy. Of course, the idea RG is that lots of information you have on lattice shouldn't really matter. Right? They are washed out during the core screening procedure. But it turns out that some information will kind of continue, will be remembered by even at very low energy and long distance. And these are things like dimensionality, what dimension system you have, obviously, and global symmetry, and also anomaly. Okay, so let's now look at the Lipschitz magic theorem. So just to first state what this is about, this is a theorem about the low energy dynamics of spin half chain. So this was proven by Lipschitz and Mattis back in the 60s, if I remember, in appendix of a paper. And now it's we remember the appendix more than which is quite common, I think. So let's just be concrete and say we have a spin-1 half Heisenberg model with anti-ferromagnetic interaction. So Si dot Si plus 1 and S are the spin operators, spin-1 half operators. You can add other terms, plus dot dot dot. That's fine. As long as you preserve the translation symmetry and also the SO3 rotation symmetry, the spin rotation symmetry. Okay. Now the theorem is the following statement. If we consider a periodic boundary condition of this spin chain with a size L, we have L spins, and with a Hamiltonian like this, the gap to the first excited state has to be bounded by something that decreases with 1 over L, okay? Which means the system has to be gapless in some sense. All right, so that's what's actually proved. Now, if we interpret it, if we want to interpret, we can paraphrase it as the fact that this theorem forbids this Hamiltonian having a unique gap ground state. Right? That's the only scenario that violates a statement of the theorem, that you have a gap and you have a unique ground state for any size L. And given this constraint, the possible scenarios at low energy are basically two options in this particular example. Either you have a gapless kind of liquid, such as a critical spin chain, or you have spontaneous symmetry breaking of translation. You cannot spontaneous break SO3 in 1 plus 1, at least in this setup. And these are the two options. Now, for example, if you take the actual Heisenberg chain, you see the gapless spin-ons, you have a gapless spectrum, or we can have, we can deform Hamiltonian so that ground state have these dimerized, wave function, which spontaneously break the translation symmetry. I should use this one. All right. Usually in physics, when we cite a theorem, we'll skip the proof. It's just math. But in this case, actually, I would say the proof is actually more important than the theorem itself, because it contains new ideas that really open the door for many new developments. So they came much later. So I'll kind of outline the proof. Okay, and it turns out that proofs are actually elementary and simple. So it's very ingenious. So it's just the outline. So if you want to see the detail, encourage you to just fill in the gap on yourself, or you can open a book like this book by Albach, and you'll see the complete detail. Okay. All right. So first, kind of to prepare the proof, we need to understand the quantum number of the ground states. This is a spin system, so it has a SO3 or spin rotation symmetry. And it's easy to see that you convince yourself the ground state should be a spin singlet. After all, we have an anti-ferromagnetic Hamiltonian. It tends to favor spin singlet ground states with S equals 0. Otherwise, you would any other S would break the SO3 symmetry. That does happen, for example, with ferromagnetic Heisenberg, but does not happen with anti-ferromagnetic interaction. Now, for the particular case of Heisenberg and a class of Hamiltonians, you can rigorously show that the ground state must be singlet, which is known as the Marshall theorem. But let's just accept this as that the ground state is singlet. All right. Now, the idea of the proof is that of Lipschitz lattice is that let's construct, the proof is a variation. Let's construct another state, which is not eigenstate in general, but we can prove that this state is orthogonal to the ground state. So it must be a different state. And turns out that this new state, the variational state, takes a particular form. You start from the actual ground state, which I call psi of 0, and act on it by some unitary operator. If this formal unitary operator looks somewhat mysterious, we'll unpack it on next slide. And let's just say this is a variational state. And then the last step is a lot of algebra. And you can prove that this state, expectation value of the Hamiltonian, which is the average energy on that state, goes like bounded by 1 over L. Okay. So this is a state which has very low energy. Now, if we can establish the existence of such a state, then we know there must be excited states whose energy is bounded by 1 over L. Okay. So this is the proof, basically. So the key here, obviously, the second step, construction of this state, which is orthogonal to the ground state and has a low energy. Okay. So let's go to the next slide. So this operator that we use to construct this variational state is called a twist operator. If you look at it, it is a spin rotation, a bunch of spin rotation on each side. But the amount we rotate depends on which side. Right? It goes like 2 pi j over L. So there are two things to notice. One is, this rotation, the variation from one side to next is small. So it's 2 pi j over L on one side, and the next side just increases the amount by 1 over L. And that's why this state has a low energy, because you vary very slowly from side to side. It's almost like a spin wave state. Okay. Now, why do we construct this state? What does it really mean? Well, to understand it better, let's consider a slightly modified form of Hamiltonian. Okay. So in this Hamiltonian, this new family of Hamiltonians parameterized by a parameter sigma. Sigma goes from 0 to 2 pi. Think of it as angle. And if we set sigma to 0, this goes back to the Heisenberg chain. So here I only include the Heisenberg term. Other terms are ignored. And the difference is that S plus S minus, so S plus is the raising and lowering operators, S plus minus. The difference is that S plus and N minus now has a complex space in front of it. If we think of the spin 1/2 as hardcore bosons, it just means that if you hop the boson from one side to next, it hops with a phase vector. And this phase vector goes like sigma over L, the same sigma. Okay, so formally, we say that this Hamiltonian is now coupled to a background field, background gauge field, which is parameterized by this sigma. Okay. Now, the significance of this Hamiltonian is that if you set sigma to 2 pi, this is what you get if you conjugate the original Heisenberg Hamiltonian by u. I should have written this down somewhere, but maybe I'll show the whole thing. So, so h of 2 pi, when you set sigma to 2 pi, is related to h of 0, which is Heisenberg by this conjugation of u. Okay? But it's not, this relation only holds when sigma is 2 pi, not for other value of sigma. Okay. So you can say that this new state we construct, psi 1, is actually the ground state of this new Hamiltonian, h of 2 pi. Okay. All right. Now let's consider the lattice translation. So the translation symmetry plays an important role in this story, so you need to think about it. And again, by just directly doing the algebra, you see that the translation operator and this u operator has this following commutation relation. Basically, u does not commute with translation. And you get these funny vectors in front. Okay. It actually makes some sense if you think about this as a dipole operator. So S of z, if you think of it as some kind of charge, and j is a distance, so the sum here is like a dipole moment of that charge. And we know the dipole moment depends on where you start. It starts from some origin. If you shift the whole thing, it means that you basically shift its dipole moment by the global charge, which is a vector here. That's a global SZ. But actually, more importantly, there's this e to 2 pi I S1 z to really, if you work out algebra. Now remember, we are thinking about the singlet ground state. So let's set SZ to 0, at least when you apply it to a ground state, you can safely get SZ to 0. And then we just get, let's set SZ to 0, so this becomes 1. And remember, spin 1/2 has this funny property that if you rotate 360 degrees, you get -1. Right? So which means u and t anti-commute. If you apply u to a state, it changes the momentum, lattice momentum, by pi. That is why this new state, psi 1, is orthogonal to the original ground state because it has different momentum. Yes?
Does sigma here have the interpretation of a magnetic field?
Yes, that's what's drawn here. All right, so sigma is interpreted as the flux threaded through the ring. If you think of the ring as embedded into a 3D space. Okay. But because psi 0 and psi 1 have different lattice quantum numbers, they are orthogonal. So that finishes the proof of the second step. Then the last step is just energetics. So we're not going to discuss further. So this is basically how the theorem is proved. Okay. But now it turns out that it's actually very enlightening to consider this whole family of Hamiltonian sigma varying from 0 to pi. So you start from the Heisenberg chain on the ring, just the bare Heisenberg chain. Now imagine we thread this ring with a flux. This is not the electromagnetic flux, it's a flux that couples to the SZ. Okay. So it's like the U1 SZ flux. And the Hamiltonian becomes this one. This is basically the minimal coupling when you have such a flux. And when you thread flux all the way from 0 to 2 pi, you get the 2 pi over L. And the sigma becomes 2 pi. But we know when sigma is 2 pi, it's actually the same as 0. But we need to be careful about what this same means. What the same means here is that the h of 2 pi is related to h of 0 by unitary transformation. So it means that the spectrum will be the same because they are related by unitary. However, the quantum numbers of the eigenstates are shifted in some funny way. So even though you have the same spectrum, the quantum number are different. Okay, so just to make it a little more concrete, I'll show this plot of the actual spectrum of this Heisenberg Hamiltonian. So on the left, I show what's shown here is a spectrum, actual spectrum of a Heisenberg chain when you have 16 spins. And the x-axis are the lattice momentum. We just labeled it by the momentum, which is our multiples of 2 pi over L. So you see it's gapless. You have this branch that goes to 0 here and here, right? Only shows from 0 to pi. You can imagine there's another part from pi to 2 pi, which look exactly the same. So just shows the 0 to pi part. And the ground state here is spin singlet. Okay? The circle is a spin singlet. And the first excited state it sits at pi, which is spin 0 and spin 1. Okay. All right. Now on the right is the spectrum of the Hamiltonian. So now the y-axis is the energy of the Hamiltonian is a function of this sigma. I just plotted the first, a few levels of the Hamiltonian as a function of sigma. So over here, when sigma is 0, it's just a Heisenberg chain Hamiltonian, the spectrum of Heisenberg chain. Then as we advance sigma, you see that the first and second excited state cross exactly at pi, they switch role, and now this one is pi 1, psi 1, because we just said that the first excited state is here. Now they move over to become the ground state of the Hamiltonian as sigma equals 2 pi. All right. Okay. Good. So that's fine. So we have a proof of the Lipschitz-Madis theorem. What does it have anything to do with anomaly? Okay. Well, when we think about anomaly, probably the first example that comes to your mind is a quantum Hall. Edge of quantum Hall has chiral norm. So let's draw some analogy between the spin chain and quantum Hall. So the physics of quantum Hall, I'm sure everyone here knows the physics of quantum Hall. You have 2D electron gas in the magnetic field building up the lambda level, first lambda level, and you have Hall conductance, quantized Hall conductance, which means that you turn on electric field, for example. So this is supposed to be the bulk of the quantum Hall with an edge along x. If you turn on the electric field along x, the current flows away from the edge or into the edge, depending on the direction. Okay, so that's just quantum Hall conductivity. Now, famously, to interpret the quantization of Hall conductance, we would usually invoke Laughlin's flux insertion argument, which is often quickly done on a cylinder or a Cabino disk, as drawn here. So on this disk, you have two edges, the inner and outer edge. Okay? And we spread flux through the inner edge or through the hole in the middle. And there's current flowing from the inner edge to the outer edge. That's Hall conductance. Now, to see the analogy between the two systems, I want you to let's focus on one edge. Let's pretend your electron living on the edge. You don't know there's the quantum Hall bulk. You don't know there's another edge very far deep in the bulk. You're just living on this edge, and all you have access to are stuff on the edge. Okay? So you're in a similar situation as spin in the spin chain. Now, what you see is that when I turn on the magnetic field, which changes the edge Hamiltonian in a way similar to how the spin Hamiltonian is modified with sigma, the charge on the edge is not conserved. The charge goes into the bulk and goes to the other edge, right? Which a physicist living on the edge has no idea. So he would just declare that, he or she would declare that it's anomalous. There's something's going on, something very fishy is going on. Of course, we know what's going on because it's only part of the system. Okay, but if we just look at the edge, there's a very clear analogy between the two systems. You have a 1D system, which was a spin chain, but now it's just a 1D edge of the quantum Hall. And we thread some flux. We have a conserved U1 charge and you thread flux. And when you thread flux from 0 to 2 pi, the system returns to the initial configuration with the same energy spectrum. However, quantum number, the states, are modified. Here, the difference is that at the end of this process, the charge changes by 1. While in the other case, the spin chain case, nothing changes about the charge. It's the actual spin chain, it's not quantum Hall edge. However, the momentum changes by pi. Okay. So this is the sense in which these two systems are analogous to each other. As you change the flux, some quantum number of the system change. The quantum number could be a U1 charge, It could be lattice momentum. Okay, so now I'm ready to discuss what do I mean by total anomaly. I should probably have said it in the beginning, but feel free to interrupt me anytime with questions. I think I have material that's probably just an hour and a little more than an hour, so there's plenty of time. All right, so what is a total anomaly? Okay, so in this discussion, let's take a little abstract perspective. So let's not specialize to a particular Hamiltonian, particular system. Let's just say you want to study some quantum system, some local quantum system, meaning that you have some notion of local space. So interactions are local, degrees of freedom are local, and you have the idea of local observer, can probe things locally. It doesn't really matter whether it's a lattice model or it's a continuum theory. Let's just say you have a local quantum system, and this system has some symmetry. So if you have a system, of course, you identify what's the symmetry of the system. And here, the symmetry is a textbook definition of symmetry. Just have some unitary operators that commute with a Hamiltonian, otherwise it wouldn't be a symmetry. And there's some technical conditions. For example, they should act faithfully, and this is if it's not if what it's not clear what it means to be faithful means that the only thing that acts trivially is identity. The symmetry otherwise has to act on something. Then the symmetry should preserve locality, not be some completely random unitary operator. Okay, and I'm excluding, at least in this discussion, the anti-unitary symmetries like time reversal symmetry. Okay, so this is the setup to discuss anomaly. Now, once you have such a setup, a local Hamiltonian or local system plus its global symmetry, we don't even need Hamiltonian here, of course. No. Physically, we would start from some Hamiltonian and identify symmetry, etc. But let's just say the minimal ingredients are the system, local quantum system plus the symmetry. And such a system is associated with something called a total anomaly. Now, some of us, when we first learned about this subject, we probably saw claims about what anomaly means in various forms. For example, usually, historically, anomaly discussed in quantum field theory, and we'll credit to something about the divergence in field theory. Okay. Or this anomaly is about the state of a topological edge state of some topological phase, etc. If you accept what I just told you, neither of these is true for the Lipschitz-Mattis story, because it's a spin chain, there's no divergence, it's a lattice model, and clearly you can have a spin half chain without attaching it to any bulk. Right? Okay, so now with this setup, let's try to define a little more carefully what it means to have a total anomaly. Okay, so a system with a global symmetry can be coupled to a background gauge field. By that, we just mean if you have, for example, if you have U1, you attach a lead, you measure electromagnetic response. You can do it for any symmetry, at least in principle. Not sure experimentally, but at least theoretically, that's something that can be done. And we just did it for spin chain. We coupled it to a background gauge field. That's flux. Okay, so we'll on the next slide I'll discuss more detail about the background gauge gauge field, and they will come into the Hamiltonian in the form of defects, topological defects. So just think of a Hamiltonian, family of Hamiltonian with various form of topological defects coming from the global symmetry. Now, anomaly means that in this space of states with defects, you move around in this space, there's some Barry phase in quotes. There's some it's analogous to Barry phase. In some cases, it's exactly Barry phase, meaning that you move in this space of defects and travel around some looping the loop of states, it comes back with a different state. Okay. And this phenomenon is independent of energy scale. It doesn't really matter whether you look at what energy scale you look at. And more importantly, it cannot be reproduced by a completely trivial state that preserves the global symmetry. Okay. So the last part of this statement is the kind of the general version of Lipschitz-Mattis theorem. It's kind of a no-go statement that says if you have a system with non-trivial tooth anomaly, you cannot have a trivial ground state, trivial energy theory. However, there's a kind of it's a part of just a bigger picture, that is the low energy theory. Whatever the low energy theory is, it must reproduce the same response to the background gauge field, since we have set up the system such that such response is kind of built in, right? So you should be able to reproduce that response no matter what low energy theory you have. This is called anomaly matching. So anomaly matching means that there's some information which is anomaly in the UV that has to be exactly, you should be able to see it exactly in the IR, in the infrared. Even though it takes a long, RG flow to go from UV to IR, and along the way you co-screen out lots of information about the UV, but there's some information that sticks all the way to the low energy theory, and that information, at least part of the information, is the tooth anomaly. That's why, at least theoretically, it's a useful concept. So we place some, yeah.
Could you say a little bit when you introduced the concept there of anomaly in the space of defects? What are the defects you're referring to?
That's on next slide. So I'll get to that. Yes.
Thank you.
Yeah. So in general, I guess if you have some preliminary theory, it might be defined on different Hilbert states from these. So this matching, you need to also specify some procedure to map the BNR.
So that's a good question. Of course, the UV and IR series look very different, right? So what you need to do is you need to match the UV and IR symmetries at least. Okay, so typically, in the UV you have some lattice model, in IR you have a continuum. So there's no way to match the Hilbert space, right? At least there's no direct match on Hilbert space.
At least there should be embedding.
There's some embedding. Well, I don't think the embedding of Hilbert space is necessary. The more important is the embedding of, well, not the embedding of symmetry, but how the symmetries match between UV and IR. And of course, how the observables match between UV and IR. Right? We don't necessarily need to match the Hilbert space. That's probably too much to ask for. And we'll see some examples of this. Yes.
Independent of energy scale.
Right.
Also, there's a notion of UV and IR.
Right. Oh yeah. So what that means that independent energy scale means that it holds not just for the single ground state. It holds really for at least states in the large window of energy.
Yeah, the ground state.
In the case of Lipschitz-Mattis, it's actually even far from ground state, it's still true. So they mean that you can work it out in UV, in the lattice model, where you operate at much higher energy compared to the ground state, to the IR theory. You can derive whatever Lipschitz-Mattis or whatever anomaly statement there, and then the same should be true for low energy physics. So that's what I mean. Okay. Right. And in the case of Lipschitz-Mattis, it's actually, if you do it more carefully, it's true for the entire spectrum. Okay, so now let me come back to the question of what I mean by a defect. So specifically, I mean a symmetry defect. So, so a symmetry defect, well, first, what's a defect? A defect is just a localized change of Hamiltonian. So you have a Hamiltonian and change the Hamiltonian locally. That's it. The impurity, something like the impurity. We're not going to study arbitrary defect. That's an interesting question, but we're going to restrict to a class of defect that's called a topological defect. So here I use the word topological defect in a somewhat unconventional sense. When we say topological defect, you probably think about vortices or hedgehog in some ordered medium. Here I use it in a different. Here what I mean by topological defect is just a localized change of Hamiltonian. If you're in a symmetry breaking state, then such a defect in Hamiltonian will lead to a defect in the other parameter. But that's what not exactly what I mean. All right. So what it means for a defect to be topological, such a defect to be topological, it means that you can move the defects around by applying a unitary symmetry operator. Okay. So it does not really matter where you put the defect because you can move it away by a unitary operator. Now, if this is the case, it means that the defect, introducing a defect does not really change the physics locally. Okay. If you just sit here and measure the stuff around you, even though you know there's a defect, you can move the defect away by a unitary operator, and then just goes outside the region that you're looking at. So it does not affect local physics. So it's kind of perfectly fit for studying certain global aspects of the problem. Okay, so more specifically, once you have global symmetry, so let's say the global symmetry, we label it by the unitary operator U of G, and G is from the symmetry group. It's an element of that group. And the global symmetry acts on the entire system. But now let's imagine we truncate the symmetry operator to a part of the system, to half of the system, let's say. Imagine this is the infinite system to begin with, and you apply the symmetry to half of it. Because it's a symmetry, away from this endpoint, it's going to commute with Hamiltonian. Hamiltonians are local, the symmetry preserves locality. So if you are far away from this point, we're going to preserve the Hamiltonian. So once you apply this kind of half symmetry operator, the Hamiltonian is going to be the same all the way until you hit this point. That's where the boundary is, right? That's where the symmetry is truncated. So you're going to change the Hamiltonian just at that point. So we introduce a defect. But because this is really introduced by applying a half symmetry operator, you can move it around just by making this half symmetry operator longer or shorter. So that's why the symmetry is topological. So the general slogan is that if you have a global symmetry, you can introduce topological defect, and vice versa. If you have a topological defect, you drag it along the system, you apply a global symmetry. All right, so applying a truncated symmetry operator introduces a defect, a topological defect. Yes. So yeah. Right. So what's important that the low should preserve locality. So it maps a local operator to a local operator. Even though the actual form of U might be very complicated, and things here, the defect is defined by conjugating the Hamiltonian with U. All we need to know is an action on local operator. Right. For example, the U could be a finite depth circuit. That's fine. Or even not a finite depth circuit, as long as it preserves locality. We know how it acts on local operator, we can construct the defect. I was driving, so I'm sorry, I cannot comment more on this. Yeah, so you probably know what that comment is about. Yeah, but in this talk, it's going to be like fairly simple operators. So. All right.
What generation of locality? Yeah.
Locality. Okay, so if we want to if we want to be really careful, so in continuum theory, it's actually kind of obvious what it means to local. You just have local fields and derivatives. On lattice, all the systems that we are going to discuss, at least almost all the systems have a finite dimensional Hilbert space. So you have some notion of operator on each site, and then you can have operator having finite support. Okay, and these are local operators. So that's what I mean by locality. If you want to be more complete, you can complete this whole thing into a algebra operator.
Unitary that puts the defects, do they have to compete with the Hamiltonian?
The unitary that moves with the defect does not commute with Hamiltonian, since they actually move the defect, right? So just by definition does not commute with the Hamiltonian. But it's useful, as we see. Yes.
So you construct it on the closed manifold, you need to the reference point for defect.
Well, so Yes, that's a good point. So if you have a closed chain, naively you truncate the symmetry, you create two defects. Right? However, these two defects are very local. They're just localized change of Hamiltonian. Once you know how to create two, you also know how to create one. Right?
But if you do the unitary transformation, that will do the whole thing.
Yeah. So yes. That's thanks. That's a good comment. So of course, that's in this picture. You should think of it as a semi-infinite system. Okay. In reality, you can apply the procedure first to find out how to create two defects, and they are very localized. And then you just keep one of them. The other one just erase. That's how you create. And we'll do that. So, yes.
As a follow-up?
Yeah.
Does that mean it needs to be transportable?
Transportable?
Yeah, as in like, you need to be able to move one of them independently.
Yeah, you can move it one just by expanding this region by one more site. You can move each of them individually. Right. Yeah.
So when you say you truncate a unity, you just mean remove all the terms which have support on the left side?
Right. Yes. There's some arbitrariness in the truncation, but does not matter.
But is it guaranteed that it will remain a unity?
Well, of course, when you do this truncation, you want to truncate in a way that remains preserved unitarity.
I just compared to the point of view of modifying Hilbert space instead of modifying.
So the point of view of modifying Hilbert space is more natural in the continuum field theory setup. I think a really equivalent point of view is twisted boundary condition. Here, I introduce topological defect as a changer to the Hamiltonian. You can also think of just changing the boundary condition. That's more like changing the Hilbert space. But they're equivalent as well. Right. Okay, so let's now do it in an example of spin chain. If this description of defect is somewhat unfamiliar, let's do this exercise. Okay, the symmetry I'm going to consider is a global SZ rotation. Just sum over all the SZ on each side and then rotate the entire system by amount of sigma. That's a unitary symmetry. And we apply it to half of system, as I just said. Okay. And it's going to commute with all the terms. So each of this is a spin, all the terms inside the dashed box, but on the boundary, you're going to change the Hamiltonian. Change it exactly in this way by sigma. Okay. Now, on the previous slide, I had sigma over L. Here, on each link, here I had one sigma just on this link, but it's sigma. And this is obviously 2π periodic, right? So sigma enters as e to the I sigma, so it's 2π periodic. And the problem with this Hamiltonian is that it's not manifestly translation invariant. We introduce a defect somewhere, so it breaks translation symmetry. While the earlier of the talk, I introduced this other form of Hamiltonian, where I spread the sigmas on all the links. Each of them has sigma over L. So this Hamiltonian is translation invariant, but it's not manifestly 2π periodic. Okay? So there's a kind of a trade-off. Either you want to preserve periodicity of sigma explicitly, but then you lose translation invariance, or you lose the periodicity, but translation invariance is manifestly preserved. Okay, but these two are related by this twist operator U, basically. When sigma is 2π, you can relate it to sigma is 2π here, and then it's just original Hamiltonian. When sigma is not 2π, you can define a similar twist operator, but then the best you can do is to localize, to kind of push all the twists onto one link, and that's this term. Okay, so why do we bother to introduce these defects? Well, so defects, at least for me, it's really just a kind of a way to discuss, background gauge field. Okay? And we've seen examples in spin chain. This defect is just a way to talk about the magnetic flux in quotes, threaded through the ring. Okay? And we can probe anomaly using these defects. So there are a few ways that it can happen. So I'm just going to discuss these examples. The first way is how it shows up in the spin chain and also on the point power edge, is that the symmetry is labeled by some periodic parameter, like a U1. Okay? So it's periodic. So Hamiltonian should be invariant once you shift this parameter theta by 2 pi. However, the system some other quantum numbers may not be exactly invariant under this shift of theta by 2 pi. And this is, in a sense, Laughlin's flux insertion argument. Okay, there's another way that the anomaly kind of shows up, is that once you introduce this defect, okay, we can ask how the symmetry of the system is affected by the presence of this defect. Generally, this presence of the defect actually changes the global symmetry. And can ask how the system with the defect, what's kind of representation of that symmetry, the new symmetry that you have. Okay? Sometimes the representation is projective one, then it signals anomaly. There are some other more subtle ways anomalies can arise, but we'll discuss it when it shows up. Okay, so much time do I have? I guess not much. So I'll skip this part.
You don't have to skip because we've already done some questions.
All right.
So we can.
Okay. Well, since I'll actually use this later, so I think it's probably good to discuss since we are not so constrained, as I was just told. All right. So we discussed lattice models a lot. So let's now look at a field theory. Okay. So this is the only field theory that I will discuss. It's a free boson in 1 + 1D. It's possibly the simplest field theory that you can imagine. And it's more commonly known as a Lattinger liquid. Now, so the Hamiltonian of this Lattinger liquid is this one. So the theory has the angular variable theta and another one phi, and they are conjugate to each other in this sense. So phi acts as a momentum, or conjugate momentum of theta. Okay. And they're both periodic. So phi is 2 pi periodic, and theta, they're both 2 pi periodic. The Hamiltonians are just the derivative square of these variables, the kinetic energies of these variables. Okay, so it's a very simple Hamiltonian. It's basically a free theory. Now let's discuss the symmetries of this theory. So since only derivatives enter, the theory has two U1 symmetry. One of them is basically shifting theta by some amount, but it's 2 pi periodic, so it's a U1 symmetry. And this is the second one here. It's I'll call it U1 winding or vorticity. And the other symmetry is shifting phi by some amount. Not going to change the Hamiltonian, so this is what I call the U1 charge, or U1 momentum is actually related to the momentum. So it's the density of that U1 charge is the derivative of theta, the density of the vorticity is the derivative of phi. And there's another symmetry that flips the sign of both variables, but this is not going to play a particularly important role. So the entire symmetry group is 2U1, and then there's a Z2. Okay, at least for generic value of the Lattinger parameter K. Okay, and oftentimes, when this Lattinger liquid is realized in a lattice model or in some physical system, it comes with some deformation. It's not exactly the free theory. So the simple deformations, the sign-Gordon type. For example, if you have an array of Josephson junction, you can realize a Lattinger liquid, but with deformation, or like in XY model. So it depends on the parameter K. So when K is in my normalization of the Lattinger parameter, when K is 4, this is a BKT transition. And when K is bigger, or when K is smaller, it's actually, I think it's the other way around. The other way around, sorry. It should be irrelevant on this side and it's relevant on this side. So it's completely flipped. So we should imagine this is 1 over K and this is the order, and we'll be fine. Just redefine things until it's right. And I guarantee that you can do it. So okay, it should be here that cosine theta is actually irrelevant. Remember, the cosine theta breaks that winding symmetry. So the symmetry is not there in the Lagrangian, in the Hamiltonian, but it emerges at low energy when you have this term irrelevant. And when it's relevant, it just gaps out the system and becomes a gap state. The entire Lagrangian liquid is gone. Okay, so this is, for example, this theory would describe the physics of the XY model on the rotor chain. And notably, only one of the symmetry is exact, right? Only the symmetry that shifts phi is exact. The one that shifts theta is broken by the irrelevant perturbation. Well, possibly irrelevant perturbation. Okay, and that has a reason, has a good reason. So the two symmetries are anomalous in the sense that, exactly in the sense that I introduced earlier. So you can, for example, introduce the symmetry, a defect of the U1 charge symmetry, okay, which is going to be labeled by some parameter eta m from 0 to 2 pi. It's a 2 pi periodic. And this is going to be the way to introduce a defect. Best way to introduce defect in this theory is just to shift the derivative of phi term by eta over L. This is kind of like the spin chain Hamiltonian that first introduced, okay? Because we don't want to introduce some singular delta interaction. It's best to spread it out. Okay? Again, you have the same problem. This Hamiltonian is not exactly 2 pi periodic under shifting of eta by 2 pi. Okay? But it doesn't mean that the physics is not 2 pi periodic. It just means that when you shift it at 2 pi, you also have to do a unitary transformation to bring it back. Okay? And the unitary transformations, if you just stare at this, you notice that just the integral of theta. But remember, theta is charged under the other symmetry. So when we bring the Hamiltonian back to its original form, the price you have to pay is that the charge of the system has to change. The unitary changes the charge by 1. So the 2 pi periodicity and the charge of the other symmetry, you cannot have both of them. You have to sacrifice one of them. And that's a chiral anomaly of these two U1 symmetries. Okay, so let me just add a few remarks. First of all, by now there's a fairly complete understanding of this anomaly in a setup of relativistic field theory, and there's a nice relation with symmetry protective topological phase. I guess you probably hear more about this from Xiaogang in his lectures, and its generalizations, much broader generalizations. Now, just a second remark is that if the symmetry is the internal symmetry, we can actually compute these anomalies by a purely local computation. You don't have to think about boundary condition, whatever. We can do a local computation, extract anomaly. Okay? And that's at least complete for spin systems or bosonic system in 1D. But it's not clear how to do this for spatial symmetries. All right, so now I'll introduce at least a formulation that incorporates, at least to us, incorporates internal symmetry and spatial symmetry on somewhat equal footing. Okay, and the idea is to formalize all of these things that we just said using a partition function. It's called a defect partition function. Okay, so now it's useful to think about the system evolving in space-time. So the circle is my your spin chain, and the edge of quantum Hall or whatever 1 + 1D system, and it's evolving in time. So the cylinder is evolving in the time direction, imaginary time direction, in order to compute the partition function. So along the spatial direction, there's some defect, or you can imagine twisting the boundary condition by G of the global symmetry. And since it's a static defect, it's going to just sit there. So it's a straight line vertically in a time direction. Now, I can also introduce a defect line in the time direction. But from Hamiltonian point of view, this line is just applying a symmetry operator to the state. So a line along the time direction is a defect. A line parallel to the spatial direction is a global symmetry in this setup. Okay, so this will be called G, and the temporal line is called H. Okay. Now remember, we want to do a partition function, so this cylinder should be closed up. So this line H should become H when it comes down. That imposes a condition that the G and H should commute. Only when they commute, you can define this defect partition function. Okay, so here's the definition of a partition function. So if you ignore this H, it's just the usual definition, e to beta H minus beta H. Beta is the inverse temperature, and we trace it. Now I write H of G because we introduce this defect. So just to emphasize that there's a defect in the system, I'll just write it as H of G. And then there's another operator inserted into a trace, so that's H. Again, it comes with the parameter G because, as I mentioned earlier, introducing a G defect may modify the symmetry of the problem, so you have to take that into account. But at a zeroth order, you don't have to worry about the G dependence. Okay, so this is the defect Hamiltonian. The physical meaning of this is basically like we're measuring H, the charge of H in a thermal state. That's what it means to have this defect partition function. Okay, so we have this SO3 defect. So now we're going to apply this defect partition function in the case of spin-1 half chain. So remember that we introduced this defect, e to the I sigma as plus as minus at a particular link labeled by big J. Okay. All right. So as I already emphasized, this setup this chain with a defect does not commute with translation because as you translate, you move the defect. However, you can recover translation symmetry by remembering that the defect is topological, right? You can move the defect without actually moving everything else. You just move the defect by extending the symmetry operator one more site. Then you bring it back. So pictorially, if we have a defect like this, okay, you translate, move to the next site, next link. So it's different from where we begin with. But now we apply another symmetry operator just on this site, bring it back. So we can define a new translation operator that is the original lattice translation followed by e to the I sigma sz on one site, j plus 1. And this will commute with Hamiltonian. Okay.
So basically interpretation is that you rotate half of the system of spins and the other part is not rotated.
Well, so remember here, so yeah, that's how I introduce the defect. But in this case, you just want to have one of them. You don't want to have two of them. Okay. So I just wrote down Hamiltonian where I modify the Hamiltonian on this link exactly in the same way that will be modified if you apply the symmetry to one side. But we don't introduce the other side because it's just a change of Hamiltonian. I don't have to do both of them. This is the difference between like a trivial or a non-trivial background gauge field. So in the end of the day, it's just a change of Hamiltonian. Okay, you can forget about where it comes from. It's just change of Hamiltonian. This is just to motivate how that change is done. But in the end of the day, we have a Hamiltonian with defect, and it has a new translation symmetry. And you define it as an original translation followed by the e to I sigma at one site. That also kind of explains why there's this one single site that's special in the proof of Lipschitz matrix. But again, it comes with some price, right? To recover it, we have to modify this new e to I sigma. And now if you work out translation to the L's power, translate L times, it's supposed to be periodic, but it's not exactly periodic because it comes back with e to I sigma sc. As versus t to the L equals 1 in the untwisted or the chain without defect. So this is a typical example of a defect somehow changes the symmetry. Okay, so now let's apply this defect partition function. But consider the defect partition function in the spin-1 half. So what I'm going to do is I'm going to introduce a defect. Remember that defect corresponds to the SZ rotation symmetry. And by the way, this is exactly a setup considered by Masaki Oshikawa, although it wasn't formulated using the language of partition function. And we'll we'll insert this operator T in a time direction. There's no problem inserting the global symmetry operator in time direction, even though we don't know how to twist the spatial direction by translation. Yes.
So I'm trying to remember when you inserted the motivation of the spin chain.
Yes.
Here, I remember you modified the Hamiltonian every single term.
Yeah.
So here it's only modifying one term.
So there are two.
This sigma is the same as the other sigma.
Yes. Yeah. Oh, well, it's actually the same sigma. It's actually the same sigma, but there are two gauge equivalent ways of writing Hamiltonian. One is you localize the defect at one site, one link, just sigma. The other one is you spread it out evenly over the entire system, so it looks manifestly translation variant.
But like this new sigma is like a sum of geometry.
Yes, right. So no, if you have two Hamiltonian, if you start with a Hamiltonian that you have some sigma on each link, you can do a gauge transformation to bring into a form where all the sigmas are summed up and put it on one link. Yes. Okay.
So another question. So T of sigma is basically the symmetry of your modified Hamiltonian H of sigma.
T of sigma is a symmetry of H of sigma. Yes.
And it also shifts your defect.
It shifts the defect, but then it was brought back by the e to the I sigma S1, Sj plus 1. So that's why the T now becomes sigma dependent. Okay, so this is the quantity, right? It's just e to the I beta and T, and we can work out its properties. For example, we can show that it's going to be symmetric with respect to sigma minus z of minus sigma, the same as z of sigma. And this is because the Hamiltonian actually has SO3, not just has the U1 as Z. You can apply the spin flip and change sigma, sign of sigma. And the other one is because T to the sigma has this I to the sigma S of J plus 1 on the previous slide. And remember, S is a spin 1/2 operator. So once you advance sigma by 2 pi, spin 1/2 picks up a minus sign. That's the same minus sign that featured in the proof of Lipschitz lattice. That means the partition function will pick up minus sign when you change sigma by 2 pi. Okay? So as a function of sigma, this partition function is kind of a weird function. Right? It changes by -1 if you advance sigma by 2 pi, but on the other hand, it's also kind of symmetric. Okay. Now let's set sigma to -pi. Just put sigma equals -pi here. So the first one will tell you, z of -pi is equal to z of pi. The second one will tell you they have to differ by a minus. So z of pi sigma, z of beta at sigma equals 0. And that's because you actually have two states that cancel each other in this trace. If you remember this picture of spectral flow, the level crossing happens exactly at sigma equals pi. And that's a two states that cancels each other when you put them into a trace. Okay, but no, now we don't have to solve Hamiltonian, just derive it from very general consideration. And here's a kind of argument for Lipschitz lattice. If there's a unique gap ground state at sigma equals 0, that's the Hamiltonian, when we expect that introducing the sigma should not really change it suddenly, right? Because you introduce it 1 point. It's hard to imagine that somehow this 1 point is going to entirely change the Hamiltonian, especially when it's gapped. So we should expect that the unique ground state for every sigma. However, we just show that it cannot be the case. Otherwise, you would have z of sigma well-defined, non-zero for every value of sigma. Okay? So that's a contradiction. And essentially, this is rephrasing Ishikawa's argument, the proof that we just introduced. All right, how many minutes? Or I'm just final remarks. So I'll have to leave out the last part, or maybe just show a couple of slides. Yeah.
Maybe 3, 4,
okay.
5. Yeah,
okay,
you
thanks.
can expand more than final.
All right. Beyond final remarks. So first remark is that, this is actually a remark. First remark is that the whole argument I just showed on the previous slide only relies on looking at sigma equals pi and having this symmetry. That's important to derive the two conditions on Z. So you don't really need SO3, right? All you need is the two symmetries that allow you to define the defect at sigma equals pi. That's a Z2 symmetry. That's a pi rotation. and the other pi rotation that flips the sign of C. Therefore, you don't need a full SO3, just need, it's a discrete subgroup of just pi rotations. Okay, so this actually holds much more generally. You don't need a full SO3. And there's a further generalization for any symmetry group. All right, and further generation, higher dimensions, replacing translation symmetry as point group. Now we've understood a lot about what these theorems are, and what they imply in dual dimensions and higher. Okay, so this part I'm going to skip. Just going to mention quickly the last part of what I was supposed to discuss is that while we have, this was a kind of a motivation slide that we want to understand the relation between the lattice and the continuum, or the IR physics. And lattice has some symmetry. We've talked about the symmetries of lattice model. Now, IR theory, the QFT, usually has a larger symmetry. Right? It's a continuum theory, so it has continuous translation, rotation symmetry. It usually has more internal symmetries as well. Okay, so now in this particular case of a Heisenberg chain, the UV system, the spin chain, just has SO3 times translation, and then maybe time reversal and parity, but let's focus on these symmetries. The IR theory, for those who are familiar, this is the SU2 level 1, Westermann-Witten model. There's a much larger symmetry, the SO4 symmetry. Okay, there's a vector, 4-component vector you can rotate, consists of the new order parameter and the VBS order parameter. But this is only a symmetry in the IR. Much of it is broken by irregular perturbations down to the actual symmetry. Okay. Now, there's an exception to this statement. There's one element in the 4SO3. There's one element of the 4SO3 besides the SO3, which embeds into the SO4 as a diagonal SU2. There's one element in the whole SO4 that is actually exact in the IR theory, meaning that not broken by any perturbation in the IR theory, in the low-energy theory. However, it does not come from any of the symmetries here. Okay, well, it does not come from the SO3, even though the C is an internal symmetry. It does not come from the SO3. It comes from the lattice rotation translation. And we feel that there's a need to have a distinguished name for this symmetry, and we call it eminent symmetry, emanated from the lattice symmetry and becomes an internal symmetry in the IR theory. Okay, so given the time, I'm not going to go through this whole thing, but I want to show you one plot that kind of explains why we discuss this whole stuff. And this is a plot. So why this symmetry is important, C is important. So the importance is that C actually, this eminent symmetry has an anomaly on its own. Okay? It's different from this Lipschitz-Mathias anomaly because the Lipschitz-Mathias anomaly involves a spin rotation symmetry, and C just comes from lattice translation, becomes a Z2 symmetry in the IR theory. Now, it's a symmetry that's only really present in the IR theory. So naively, we don't expect this symmetry to have anything to do with the lattice information, right? It's a symmetry that's only there in the IR theory. It turns out that this symmetry somehow also shows up even when we look at very lattice-like quantities. Here's what it is. So if we diagonalize a spin-1/2 Heisenberg chain, just on a computer, I showed you earlier the spectrum of L equals 16. So it's better to look at even number of spins, otherwise it would have degeneracy in the ground state. So for 16 spins, the ground state, finite size system, the ground state at momentum 0, first excited state at momentum 5. If you just change L by 2, you find that the ground state now suddenly shift to pi. And kind of these two states just switch over. Okay. So remember, this is not doing flux insertion. This is actually changing the size of the system, going from, and then suddenly the momentum of the ground state changes. And it kind of keeps going. So if you increase it by 2 again, it comes back to 0, vice versa. Okay. So now this is a fact that was known for a long, long time. The earliest reference I can track is a paper in 80s by Sharsky, who just said it without any reference, as if it was like known to everybody. I was told that this was already noticed by Beta in his Beta ansatz paper, but Beta's paper was written in German, so I gave up. I tried, I gave up. All right, but so I would, if anyone can tell me where this was first noticed, I will be very grateful. But this curious fact about the ground state momentum of spin chain actually is explained, which apparently I don't have time to discuss, but is explained by the anomaly of this eminence symmetry. So somehow we see kind of the two ways interaction between UV and IR. We see that the Lipschitz-Matisse anomaly in the UV constrains the dynamics in the IR, and in the other direction, the anomaly of this eminence symmetry, which only exists in IR, also feeds back into UV, and it comes out as changing the lattice momentum. All right, so I think I'll just conclude here, and thanks for your attention.
Any questions?
I think also the example you gave at the mixed anomaly into symmetries.
Yeah, but this last one is not.
So how do you construct the defects for the?
In this particular case, it's a defect of the, well, first, but the C is a part of the SO4 symmetry, right? In the case of Luttinger liquid, it's really just doing a pi rotation in both U1s. So we certainly know how to construct defect of that symmetry. In the field theory.
And you can also say that after you do this, you use the unitary to relate the transformer Hamiltonian to the original Hamiltonian. You can also say that this chart be shifted.
It's more subtle. First, we cannot relate the two Hamiltonians because with a defect, without defect, right? They are different Hamiltonians. Also, what the anomaly is really about is this picture. That if you have two C defects, you fuse it, and they should annihilate each other, but that will change the C charge of the system. So this is how the anomaly is defined for the C symmetry. That fusing the two C defects changes the C charge. And the reason that C is a pi flux, basically pi flux. Using two of them is like inserting a 2 pi flux. That changes the charge. It's kind of a remnant of quantum Hall response when the symmetry is just C2.
Any other questions?
Yeah, so in the last example, we're adding two lattice sites. Reflecting a twist, then you measure momentum shift by pi.
Yeah.
Yeah, I understand that way.
Oh, yeah, that's this picture. So each C line is a lattice site. So two more sides is two C lines.
Oh, okay.
And now to relate them back, can fuse these two C lines.
Okay, yeah, thank you.
There was a hand.
So you said the eminent symmetry is a property of the low energy theory,
right?
Not just the ground state. The consequences that you derive are mostly for the ground state. Right. Is there a way to infer something about the low energy spectrum from eminence? Not just say the standard
standard consequence of symmetry.
Like usually we say when we have a symmetry, we're still classified.
Yeah. Well, so in this case, we can say that if you have a spin chain of all number of sites, the spectrum agrees with the low energy theory with a single C defect. The low energy spectrum agrees with whatever the CFT with a single C defect. That's something you can say.
So just a quick question about the compact boson or the free boson example. When you introduce the defect of the U1 sub-M symmetry,
right?
Wasn't that basically the same as just using a gauge flux of the U1 M symmetry?
Yes. Yes. In this case, it's a flat background gauge field. In 1D, of course, you can only have flat. It's supposed to be a flat background.
in this picture, if you insert one C vertical line, that means inconsistency. These two you cannot do that. Or means kind of non-invertible symmetry involved.
No, C is an invertible symmetry. Introducing a single C line is the same as having all number of spins. So the spectrum of the Heisenberg chain, for example, with all number sides is described by the SU2 level 1 with a C defect. So there's no inconsistency. At least.
But so therefore the configuration of if the single vertical C line is allowed. It's
yes,
not like a G and H do not commute.
It is allowed. It is fine. C commutes with each other. Yeah, that's fine. So so it's more like you rotate this picture, rotate space and time. So what it said that in the presence of a single C line, C squared equals -1. But that's also a known fact about the super level.
All right. If there are no further questions, let's thank our speaker one more time. We'll have one more quick coffee break before having our final speaker of the day.
This three lines that relate to this.
Hey, see you.
You're going to basically.
Yeah, actually, I'm going to. Well, supposed to go see Nadi at the institute, but maybe in some 10 minutes after the coffee break. Yeah, sure. Yeah. Okay, I'll find you when I head out.
Yeah, but that's related to this self anomalies.